What's up, guys? You're on Differentiation A-Level Maths with Daniel Dallas. Alright, so yesterday, as you remember, we covered the basics, how to find the gradients of the chord, how to find gradients in a given point to the curve. That was tangent, actually. And we also had a look, what if your chord, so simply the line segment that connects 2 points, for example, like P and Q, right there on this graph, on this diagram. What if in the case Q tends to the point P? Actually, the gradient becomes the gradient of the tangent. Okay, so that's why it's right time quick to recap the gradient of the chord right now. Let's do it quick. So what do you need to do? You need to find the gradient of the chord PQ. So first, let's set up the coordinates for P. It's 1, 1. For the point Q, we also set up 2 and 4. And make sure you remember, if you give an equation, as in this case, fx equals x squared. In case if you are not given, let's say y coordinates like 4 and 1 here for those 2 points, you can easily calculate by plugging x coordinates into the function instead of argument. All right, so make sure you understand this principle of just functions. Okay, so let's try to work out the gradient. So the gradient of the chord PQ is going to be equal, let's put this line right now, line segment from point P to the point Q, okay, right there. First of all, I show you just algebraic way, that's change in y coordinates of the points over change in corresponding x coordinates. So in our case, it's going to be 4 minus 1, that's change in y coordinates, and delta x is simply 2 minus 1. So finally you get 3 over 1, which is 3. Another way how you can do it graphically, just remember how to work with straight lines. So just remember, PQ is the part of straight line. So we just arrange triangle similar to what you see here. And we set up the change in x coordinates. So simply this delta x is going to be 1 from 1 to 2 and delta y, okay? So this is an alternative way how to find the coordinates, changing coordinates. So from 1 to 4, which is 3. So now you're doing the same, and the gradient is going to be 3. All right, so that was quick recap. For those who are not sure how to do that, just please watch the video. That was the basic video in differentiation. And now we're gonna go to differentiation from first principles, or sometimes aka as differentiation from the first principle. So what's the first principle? It's just differentiation by definition. In other words, you need to find derivative of the function. In other words, that's the gradient of the function at a given point, just by definition. All right, let's consider this picture. So you have point P and you have point Q, and you see that we have the chord P and Q. But in this case, I set up general coordinates for that. So let's have a look there. So P has the coordinates x, and to find actually y coordinate, we simply need to put this x into the function. So your curve has an equation fx. That's general equation. Okay, so you just simply need to put this x inside your function as the argument and calculate f, in other words, y value. Okay, let's have a step of h. So it's denoted here. From there, let's take another color. Let's take that one. Okay, so we made a step of h to in attempt to arrange triangle, right angle triangle. Okay, so we also need to make a change in the function, which is simply represent change in f. In other words, point Q will have x plus h coordinates because we made a step h. This is just simply denote horizontal step. So this delta x, as you remember from the previous picture, so that's delta x, simply becomes h. And change in y coordinates simply becomes f from the x plus h minus fx. So that would represent delta y. Okay, so let's calculate the gradient for the PQ, for the chord PQ. Just by definition is going to be change in y over change in x, but change in y represents function at a given point x plus h, so at this point x plus h, and you subtract the y coordinate of the point P, which is just simply fx, okay? Then you divide by change in x, which is horizontal step equals to the h, which is denotes, change in x coordinates of points P, between points P and Q as h. Okay, and that's what we have. This is sort of general expression for the gradient PQ. If you have initial point P with the coordinates x, and because it lies on the curve, the y coordinates will be defined just by plugging arguments instead of function, right? Okay, and point Q, in a similar way, will have, because we made x plus h steps, so now x coordinates is x plus h, while y coordinates is simply, again, you take in this argument and put instead of x right there into the equation of the function. So that's why the argument will be new one, f from x plus h, okay? And you just go by definition what gradient is. Okay, we did it. Now let's explore, let's go to this diagram and try to play with gradients. So what if you start moving your point Q, remember we did it in the previous video, we try to approach point Q to the point P just right along the curve, like this. And you understand that the gradient of initial chord PQ start decreasing until it actually will be equal to the gradient of the tangent line, right? So let's pretend, so I put this T as the tangent line. So I mark as the tangent. So this is the tangent at a given point x. So we have a tangent to the curve, right? Tangent to the curve. Okay? So that's why if we start moving point Q to the point P, your gradient of PQ becomes equal to the gradient of the tangent, okay? And what it means that we move Q to the point P. In other words, we're trying to diminish the step h, as you remember. So one more time. So we had step of somewhere here, I guess. Yeah, we had step of horizontal step h here, and that means by moving point Q right to the point P, we try to diminish this step up to 0, right? Because only in 0 case, when h is very, very, very small, we will arrive to what? We will arrive to the point P. So Q, in this case, will arrive to the point P. So that's why it means that h step, horizontal step, should be very, very close to 0. So this arrow denotes that we're taking the limiting case. H is very close to 0. That's why we can denote as the limit, okay? So that's why gradient PQ will be equal to gradient T only when h is very, very small. So that's why we can write that gradient PQ when we're taking the limit of h very close to 0. In this case, and only in this case, you'll have the gradient of t. Okay, so let's move back to gradient PQ. So gradient PQ represents the change, right, in the function, basically this change delta y over h. So that's why in this case we can apply this limit when h is very close to 0 to the expression of the gradient, which is simply fx plus h minus fx over h. And only in this case we'll get the gradient of the tangent. So in other words, you remember that gradient shows you how fast your function is changing in a given point. And because the function is like a curve, it's not a straight line, the gradient is always changing. So that's why it will show you the gradient at the point P. Or, in other words, at the point with coordinates x, right? And f from x. So that's how we can define the gradient. And that exactly means that you're trying to find a derivative, okay? So that's why if we go there, we can denote this expression. So in other words, we can denote that gradient of the tangent, we can denote as f dash, okay? F dash. So this actually apostrophe means that we're taking dash, right? In other words, this represents derivative, okay? Derivative of the function. That what it means differentiation from first principle by definition. So by definition, all right? And sometimes you might heard, okay, f prime. Sometimes you might heard this words f prime, or you might heard the words about derivative. So we differentiate the function, and sometimes many like teachers told you that it's dy dx or df dx. What those d means? It's sort of notation. However, if you have a look back to what gradient is of the PQ, is change in y over change in x. So in other words, it's change in the function f over change in x. The change in x is h, right? So that's why it would put, instead of those deltas, that means change, those d's, that means difference, okay? It means difference, okay? We will get dy dx. However, this is the same as delta f over delta x. However, when delta x is very small. In other words, there was h, right? So, because many students are really confused about notation, so I try to clarify that. And that means that you are going to use just dy dx, that means derivative. Okay? So before we go into examples, so I strongly recommend to understand those details because that's the core theoretical basis. And in the next video, we'll go through several examples where I show you how actually to apply that. Okay? Be in touch and don't forget to visit A-level classes. And thanks for watching.